right, now, remember how I told you the difference quotient was important, and we've been cranking this out for over a year now. All right, so I want to do just a nice little comparison here. All right, so we know what the difference quotient is. I'm going to abbreviate just so that it's less writing. Okay, so the difference quotient that we used primarily last year was f of x plus delta x minus f of x all over delta x. All right, now, from doing that in pre-calc, do we remember what that gives us? When I do that difference quotient, that gives us the slope of the what? Anybody know? Slope of the, not the tangent line, secant line. This gives us the slope of the secant line. Slope of secant line, okay? So, I mean, we've done it, and you've cranked it out, and we even in different class sessions, you know, focused on that at the time. And I think in pre-calc, like some of you gathered that at the time. It probably didn't go into long-term memory. Like you did, you kept doing that difference quotient, and they kept doing it of the line, and then you were like, oh, but that's the slope every time. Okay, so it happens to be the slope of a secant line when we're dealing with our polynomial curves and stuff. Okay, then just recently, what did we do? We took the limit of the difference quotient. Okay, and we did that just at the end of our chapter 1. Okay, so then we threw in this notation of the limit as delta x approaches 0, and we just put that in front, and then we started working it out again. Okay, now when I work this out with that limit as delta x approaches 0 in front, that's going to give me the slope of the tangent line, and I want to say more specifically the slope of the tangent line at any given point along the curve. So slope of the tangent line. Okay, but what did those answers look like? When we took the limit as delta x approaches 0, we didn't just plain get numbers. We got like 2x, all right, something like that. So it wasn't a numerical value when we did this. Because what that's doing is it is giving me the slope of the tangent line, but as we have our, let's look at a polynomial curve here. Let's just do a random polynomial curve, okay? Well, how many tangent lines are there? Well, there's tons, right? Because there would be one right there, and then over here, there's another tangent line. And as that tangent line, as the point at which I'm finding those tangent lines moves along the curve, then the slope of those tangent lines change, right? So when we do this, the limit as delta x approaches 0 of this, and maybe, for instance, we get something that looks like a 2x, all right? This is generic, as in it gives me the slope of the tangent line at any point along the curve. So if I know x is -3, I could plug it in and find out what the specific slope is at that point. At x equals 2, I could plug 2 in and find the specific slope of the tangent line at that point. Okay, so it gives us the slope of the tangent line at any point, so in a more generic form. All right, so what we're going to do is we're going to write the equation of these tangent lines. Okay, now normally it helps if we know the slope and we know a point, but if I ask you to write the equation of that tangent line right there, okay, well, if I tell you that's at x equals 5, okay, I've got my point, all right, and if I know what my function is, then I can do the limit as delta x approaches blah, 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 and end up with something like this and plug 5 in and then get the specific slope at that point. And all I need is a slope and a point. Okay? All right, now while I verbally explained all that, and that may have sounded a little bit confusing once we start doing this on paper, it's not going to be. Okay, so let's crank out an example. The directions, I'm going to write the directions because this is the first time we've done it. You'll see a variety of different directions. I think your book just likes to say using the definition, all right, but to me that's kind of vague. But your textbook does that, all right? I want to put in parentheses using the limit process, because that's kind of what IU likes to put on their test. So those two phrases are the exact same thing. Your book is going to say using the definition. IU exams usually like to say using the limit process. Find the slope of the tangent line at the given point. Can we do this as a two-parter? Then write the equation of the tangent line at that point. So I'm kind of combining two questions here into one. That way we can just do one example maybe, and then move on to something else. All right, so let's say they give you a nice little function. Let's say the function is f of x equals, I'm going to keep this function relatively small so that, because you know how to do the difference quotient. We've done it tons and tons and tons. So nice little baby function there of an x squared minus 9. And then let's say at the point 2, -5. So they've given you the specific point. I know the point. So if I've got to find the slope, I can find the slope at that point, and then I can find that equation of the tangent line. All right, so let's do this in 2 steps. I want to outline this a little bit. All right, the first thing I got to find is the slope of the tangent line. Okay, so step 1, slope of tangent line. Okay, so we do this by taking the limit of the difference quotient. So the limit as delta x approaches 0. All right, now we all have the difference quotient memorized, right? We're supposed to take x plus delta x and put it in for x, right? So x plus delta x to the second power, and then minus 9, and then subtract the function. So minus, I'm going to put a set of parentheses in the entire function, x squared minus 9, because remember we got to go through and change those signs because it's subtracted the entire function, all over the delta x. So I'm going to hope I can get this all on one piece of paper. The limit as delta x approaches 0. All right, can we square this in our head really quick? X squared, don't let me make a mistake, plus 2x delta x plus delta x quantity squared minus 9 minus x squared plus 9. Everybody following me so far? Yeah, because this is all review. We're pretty good with this. Okay. All right, let's cross off some things. We've got an x squared and a minus x squared that we can cross off. We've got a -9 and a +9 that we can cross off. All right, so can I, in my next line, automatically go to factoring out delta x? So we've got the limit as delta x approaches 0, factor out that delta x. So I'll have a 2x plus a delta x all over the delta x. Those delta x's are going to cross out. Now can I go to a direct substitution now right away without rewriting again? Yeah, so let's go direct substitution. Plugging in 0 for delta x is going to give me 2x. All right, now that is the slope of the tangent line at any given point. All right, so slope of tangent line at any point along the curve. That's the slope of the tangent line at any point along the curve. Okay, but I don't want it at any point. I want it at this point. Okay, so x is 2. So I'm going to plug 2 in. All right, so slope of the tangent line, and then trying to make this organized. I'm going to come up a little bit so I don't run out of room. Step 2, slope at the point 2, -5. I'm just trying to write this out since this is the first time we've done this. I'm going to use this 2x. Slope is m, right? So let's try to make this look a little official. I don't know that we have to do that, but m is equal to 2x, which is going to be equal to 2 times 2. Most of you could have just done that in your head, which I'm going to get a nice little 4. So this is the slope at the point 2, -5. Okay, so it's following me so far? Okay, now what I've got to do is I'm going to take this point and I'm going to take this slope and I'm going to use point slope form. Remember how I told you we were going to use point slope form like all the time in calc? Okay, so here it comes. Now the second part of the question says then write the equation of the tangent line. Okay, so our step 3, equation of tangent line. Equation of tangent line, doing some abbreviating there so we don't have to write as much. Okay, so y plus 5 equals 4x minus 2. And then if they don't tell you to put it in a certain form, stop before you make a mistake. All right, that's good enough right there. Now, of course, if you're doing your homework and then it says write it in slope-intercept form, write it in standard form, then you got to keep going. All right, but as long as it doesn't say anything, you may stop right there. So see, all we're doing is, on this, combining everything that we've already done, because we practiced this quite a bit. All right, we've definitely practiced the difference quotient a lot in pre-calc. We've added this here recently within the last couple of weeks, and you already knew how to write the equation in point slope form. So nothing too bad here, right? Okay, all right. Now, how does this all tie into it? All right, this limit process is used to define the slope of the tangent line. I just did that. All right, it's also used to define one of the 2 operations in calculus. There's 2 major operations in calculus: derivatives and integrals. All right, now go back and think addition and subtraction. Addition and subtraction are inverse operations. Derivatives, which we're about ready to move into, and integrals, the third thing we're going to study, they're inverse operations of each other. Just like add and subtract are inverse operations. Okay, so this is going to allow us to write a definition of a derivative.